By now, we have realized that population growth can be modeled using mathematics, and we can use the population growth model or the exponential growth model for us to know the population of a given city after a certain time has passed. And again, the population growth model or the exponential growth model is given as A equals to PE raised to RT, where A is equal to the population after the growth, P is equal to the initial population, R is equal to the rate of the growth of the population, rate of growth, and T is equal to the time of the growth of the population. E here, if you could recall, E here is the Euler's constant, and it is approximately equal to 2.718. So it is assumed that you already know how to use exponential growth model for us to find the growth of a population. But there are cases where you have to find the other unknowns. Usually, given these kinds of problem, there would always be an unknown and the other variables are known values. But there will be a time where A is not your unknown. It can be your P, it can be the R, it can be the T. And now I'm going to teach you how to solve for the unknowns if you have to find the initial population given the population after the growth, given the rate of the growth and the time of the growth, or maybe even you have to find the rate or time given the initial population and the population growth. So let's try to solve for P first, the easiest among the other variables that we have. If the problem asks you to solve for P, given this population growth model or exponential growth model, it is very easy for us to solve for P, because what we just have to do is to isolate P in one side of the equation and then the rest of the variables on the other side of the equation. So given A is equal to P times e raised to RT, so let's try solving for P. Okay, how do we solve for P? First, we have to isolate P, right? And it's very easy for us to isolate P because given the initial formula A equals to PE raised to RT, we only have to divide both sides. We need to isolate P by dividing both sides with this term e raised to RT. Okay, so if we divide both sides with e raised to RT, now why do we have to divide both sides with e raised to RT? Because we want to keep the equation as it is. We are not violating any algebraic rule or law by doing this. We are keeping the equality of the equation if we divide both sides. That's why we have to divide both sides by e raised to RT, because essentially what we are doing is making this equal to 1, right? A number or a term divided by itself is equal to 1. So essentially, this would become P times 1, which will leave us with A over e raised to RT equals to P times 1. And this is essentially P equals to A over e raised to RT. And that's how we solve for P if P is our unknown variable. Very easy, right? A is equal to PE raised to RT, and if we have to solve for the initial population, we just have to divide both sides with the term e raised to RT to isolate P, and you have the formula already to solve for P. Now the tricky part comes into play if we want to solve for R and T. Okay, solving for R. Let's solve for R first, because the steps to solve for R and T are just the same. So let's try to solve for one of the two first. Let's try to solve for R. Now let me write down the exponential growth formula again. So what we have to do now is to isolate r on one side of the equation and the other variables on the other side of the equation. But this is where it gets tricky because our r is an exponent of our Euler's constant, right? So how do we isolate r given that it's an exponent of our Euler's constant? Now to do that, we have to look back or dig out some of our logarithmic identities in our mathematics toolbox. Recall that one of the logarithmic identities of the natural logarithm ln e raised to x is equal to just x. So we have to recall again that the natural logarithm of e raised to x is simply x. We will use this identity for us to isolate our variable of interest, which is r in this case. Okay, so remember this identity. Now let's get back to our equation. We have a is equal to pe raised to rt, and our goal for this is to isolate r so we could solve for r. So essentially, the first thing that we have to do is isolate this term, the term that has our variable of interest. So the variable that we have to remove per se on this side of the equation is b, right? And we can do that by dividing both sides with b. So this would become 1. Again, multiplying a term with 1 is essentially itself. So this would leave us with a over p is equal to e raised to rt. Now our next step, we have to use this identity. We have to extract the natural logarithm of both sides. So we could apply this identity here, that the natural logarithm of the Euler's constant raised to an exponent is simply its exponent. So now we have to extract the natural logarithmic of both sides, which would give us ln a over p, the natural logarithm of a divided with p, is equal to ln e raised to rt, right? Because we have applied, or we have extracted, or we are trying to extract the natural logarithm of both sides of the equation. Now again, look here, this looks similar, right? And the identity says that if we extract the natural logarithm of the Euler's constant raised to an exponent, then that's simply just the exponent. So essentially what we're doing is we are removing the Euler's constant so that we could manipulate the exponent and isolate r as our unknown variable. So this, if we are going to rewrite this would give us r times t is equal to ln of a over p. Now, this is why I said that the steps to solve for r and t is just the same, because if we want to solve for r, we have to essentially what we have to do is to divide this side with t, right? To isolate r. So divide this side by t. Whatever we do on the one side of the equation, we have to do it on the other side of the equation. So if we divide this side, the left side, with t, we have to also divide the right side with t. And this would leave us with just 1. Let me pull this up, okay, so that we have space. Okay, so this would leave us with r is equal to ln of a over p all over t. Okay, and this is the formula. If we want to solve for r, this is the formula that we have to use. R is basically equals to the natural logarithm of the population after the growth divided by the initial population all over the time of the growth. Okay? Okay, to solve for t, again, Solving for t is very easy if you have already solved for r. Solving for t, you just have to divide this side of the equation with r to isolate t. So r times t is equal to ln a over p. We just have to divide this side with r to isolate t, and this would leave us with the formula t is equal to ln of a over p divided by r. And that's how we solve for the time of the population growth if t is our unknown. So just a quick recap. Let's have more space here. Just a quick recap. Given the exponential growth model, a is equal to pe raised to rt. If we want to solve for p, we just have to divide both sides with the term e raised to rt, which will leave us with a all over e raised to rt. Now, if our unknown is r, the formula for r is equal to ln of a all over p divided by t. And if t is our unknown, it looks the same as r because the process of solving for r and t are the same, because r and t are exponents of our Euler's constant. So the formula for t is equal to ln of a over p divided by r. And these are the formula for the unknown variables of our exponential growth model.